Hi everyone, thanks for joining. I'm David and I'm presenting our paper, Fairness Efficiency Trade-Offs in Dynamic Fair Division. I recently finished my undergrad at Carnegie Mellon. This is joint work with Alex Psomas, who will be joining Purdue this fall. Consider the problem of allocating donated food between different charities and food banks. The food arrives over time as it's being donated, but there's uncertainty over what food will be donated in the future, such as when grocery stores can donate food that they cannot sell. In addition, food is perishable, so it's not really an option to just hold on to all the food until you can allocate everything at once and figure out a good allocation. So translating this into our model, we have indivisible items that arrive in an online manner. Agents have values for each item, so 1 and 1 in this case, and our goal is to find a good allocation after all the items have arrived. In this case, the lamp arrives, we see the two values, and we allocate it. And we do the same for the chair and the microwave. Formally, we have T items arriving online and N agents. Agent I has a value between 0 and 1 for each item. Importantly, we only learn this value when the item arrives. And once it arrives, it needs to be allocated immediately, so we can't take back this choice. We evaluate the algorithm based on the final allocation after T rounds. Also, we assume in this paper that agents have additive valuations. What this means is that each agent's value for a bundle of items is just the sum of their value for each item in the bundle. So what makes a good allocation? In this paper, we care about both fairness and efficiency. We take fairness to mean keeping envy as small as possible. There's a few different criteria that we use in this paper. The strongest is envy freeness, which says that for all agents, they prefer their own bundle over other agents' bundles. For allocating indivisible items, a common relaxation is envy freeness up to 1 good. Approximately, what this means is that agent I would prefer their own bundle to all other agents' bundles, provided they were allowed to remove 1 item from each other agent's bundle, hence envy freeness up to 1 good. So VI, the valuation function of agent I for their own bundle AI, is greater than VI for AJ minus some item. Finally, a weaker notion of fairness introduced in the online setting is sublinear envy, which just says that the amount of envy I have towards your bundle, which is just the difference in values for the two bundles, according to me, is sublinear in T. For reference, in the worst case, it is possible for envy to grow linear in T, say if you give all the items to one agent. Note that all the other agents will have envy towards that agent that grows with the value of all the items, which could be linear in T. So still this fairness criteria of sublinear envy is basically as weak as it can get, though Benade et al. Show that this is optimal for envy in the online setting by giving a omega square root T lower bound on maximum envy. Now for efficiency, we care about Pareto efficiency. The graph on the right plots the possible utilities an allocation can have for a 2-agent problem. In blue, we have shaded the range of achievable utilities. For example, giving all the items to agent 1 is represented by the orange dot. An allocation is Pareto efficient if it is on the upper boundary of the region. In contrast, the red dot is not Pareto efficient. Now, we also use a notion of approximate Pareto efficiency. For example, consider an allocation that achieves the utility profile of the red dot. If we scale the utilities by a factor of 2, the new utility profile is Pareto efficient, so we call it 1/2 Pareto efficient. The natural question now is if we can find allocations that are both fair and efficient. Now, in the offline setting, we can achieve this by just maximizing the product of agent utilities. Karianis et al. Show that for indivisible items, this is EF1, so relatively fair and Pareto efficient. Although it's NP hard to compute, there does exist a pseudo-polynomial time algorithm that achieves EF1 and Pareto efficiency. Now, in our paper, we ask if fairness and efficiency are also compatible in the online setting. So far, I haven't really discussed how the item values, the VIT, are generated. Well, in this paper, we consider a range of progressively stronger adversaries. Now, on the right, we have our standard online algorithm adversaries, where the algorithm chooses the worst case sequence for either a randomized or deterministic algorithm, which corresponds to the non-adaptive or adaptive adversary. Now, our first result is a negative result. We show any algorithm that guarantees sublinear NV is not 1 over n plus epsilon Pareto efficient for any positive epsilon. So, to interpret this, we can show that a random allocation algorithm would yield 1 over n Pareto efficiency and also sublinear NV. So roughly we're saying that you cannot improve upon random allocation with regard to efficiency if you want to also have some level of fairness. We proved this result for the non-adaptive adversary, which will clearly also apply to the adaptive adversary. Next, we have our distributional adversaries. In this setting, item values are sampled from a distribution, but the distribution is also independent of time. We assume that the algorithm receives the distribution as input and uses it to guide its decisions. And by distributions, we refer to discrete distributions. For the identical distributions case on the left, the input is a single value distribution D. So when an item arrives, to determine its values to each agent, we'll sample from D for agent 1, then for agent 2, and then so on for all the agents. Now, with independent but non-identical distributions, each agent has their own value distribution DI. But we do the same sampling method, just from different distributions. Finally, for the correlated distribution, think of the process as when an item arrives, it is sampled from a distribution over item types, where an item type is just a vector of n values with one value corresponding to each agent. Now, for the easiest adversary, for agents with identical distributions, we can just give each item to the agent with the highest value. This algorithm achieves Pareto efficiency since it maximizes the sum of utilities, and Kurokawa et al. Show NV freeness with high probability. Roughly the intuition for this is that if I receive an item, because I have the highest value for the item compared to the other agents, I'm generally happier getting this item than the item the other agents are getting. Now, to clarify the fairness guarantee, for the 3 distributional adversaries, when we say something occurs with high probability, we mean that if we fix a distribution and then take t to infinity, the probability of NV freeness will approach 1 at some rate. Now, for this special case of when d takes on a single value, so that's like kind of the special criteria of if d is not a point mass, if it takes on only a single value, we can't hope to achieve NV freeness with high probability anymore. But we can instead actually guarantee NV freeness up to 1 good by using the round-robin allocation algorithm. So in either case, we have some fairness guarantee. So what happens if we try to extend this very simple algorithm to the stronger adversaries? For example, what about when agents' distributions are no longer identical, but still independent? Since we now need to normalize between different distributions, one reasonable approach would be to give each item to the agent for which the value of the item is in the highest quantile for the distribution compared to other agents. So unfortunately, while this still can guarantee fairness, it's not going to be Pareto efficient. So consider a situation with 2 agents, one who has a range of values for each item from 0 to 1, and one who's roughly indifferent between items, so say from 0.4 to 0.6. Now, the intuition here is that agent 2 would actually be happy to trade items that are high quantile for both of them, so worth 1 and 0.6 respectively, for items that are low quantile for both of them, so worth 0 and 0.4. And such a trade can actually improve both agents' utilities, which means it's not Pareto efficient. So even with uncorrelated agents, it's already kind of unclear who should receive an item given our knowledge of the different distributions. Our second result applies to correlated distributions. We give an algorithm that guarantees expost Pareto efficiency, and also a similar NV guarantee as we gave for the identical distributions case. So for each pair of agents, either we can guarantee NV freeness with high probability, or EF1 with probability 1. Like with identical agents, part B kind of handles cases where it's not possible to guarantee part A. In contrast to identical agents, this either-or setup applies pairwise rather than for all pairs of agents, which makes sense keeping in mind that previously all agents had the same distribution. Now in order to prove this theorem, we first prove a result for the offline setting. Specifically, we prove a result concerning the fair division of homogeneous divisible items. Divisible meaning that you can allocate fractional amounts, and homogeneous meaning that agents only care about the fraction of an item they receive. Roughly, we show that you can always find a Pareto efficient allocation that is also close to, but being strongly envy-free, but not quite. Both the offline and online result have this two-part guarantee, which relates to how the offline result is used to prove the online result, with parts A and B corresponding to each other. Next, I'll explain the guarantee in the offline setting in a bit more detail. So we call this guarantee CISEF, or clique identical strongly envy-free. It can be thought of as a relaxation of strong envy-freeness, which is when each agent strictly prefers their own bundle to the bundle of any other agent. This contrasts with normal envy-freeness, where equality is allowed. Now I'll describe an allocation that satisfies this property. Suppose we're trying to allocate the 3 items. On the right, the 3 agents represented by circles. And remember, this is in this offline setting where items can be fractionally allocated. We give the chair equally to agents 1 and 2. We give agents 1 and 2 a quarter of the fridge and give agent 3 the remaining 1/2. And now we give the microwave completely to agent 3. So how can we check if this allocation guarantees CISEF? Well, one way to satisfy CISEF would be if the allocation itself were just strongly envy-free. So if there are strong envy-freeness edges between all pairs of agents. However, this allocation clearly does not satisfy strong envy-freeness. Note that agents 1 and 2 actually have the same allocation, so they must value each other's bundles equally. Luckily, the edges between agents 1 and 2 fall under the second condition of CISEF, where they have identical allocations and the same value for the items allocated to them. Looking at the table on the left, note that agents 1 and 2 can disagree on the value of the microwave, so they say it's either worth 0.01 or 0.02. But they weren't allocated any fraction of it, so that doesn't matter. But they must agree on the value of the chair and the fridge. So they have identical allocations and identical values for the items they have. We can verify the other 4 edges satisfy strong envy-freeness, and thus the allocation is CISEF. So why do we call it CISEF? The reason is that we can actually just group agents into cliques where any edge between cliques is always going to be a strong envy-free edge. And within a clique, because agents have identical allocations and valuations, in some sense, they're kind of just like one large agent. So it's almost strongly envy-free. Why do we introduce this new definition of fairness? Well, strong envy-freeness is a desirable property in isolation and can be achieved unless all agents have identical value functions. And if we could achieve this, we could then use this property in our online algorithm for some good results. However, it's not actually compatible with efficiency. In contrast, we define CISEF in a way such that it is compatible with efficiency. Now I'll discuss how we reduce the online problem to the offline problem. At a high level, first, given the distribution as input for the online problem, we'll transform the distribution into an offline problem and solve it. Specifically, given a distribution over item types D with support gamma 1 through gamma m, we treat the item types in the support as actual items for an offline problem. And we're going to apply some scaling to the values based on the probability of each item. For example, on the left, we have the online problem distribution, and on the right, we have the offline problem that we construct. If we look at the values of gamma 1 in the offline problem, they're scaled down by 1/2 compared to the online problem. And that's just the probability that the next item to arrive will be gamma 1. We do the same for gamma 2 and gamma 3. Now, once we have solved the offline problem, we can use the solution to guide our algorithm in the online problem. Given a fractional allocation x, we're going to do a weighted random allocation. So when an item arrives with type gamma k, we'll allocate it to agent I based on the fraction agent I owned of item k in the offline allocation. So if they owned 0.4 of the item, we'll allocate it with probability 0.4. And note that by doing this, the expected utility of each agent after an item has arrived is the same as their utility in the offline problem. So things kind of work out correctly in expectation. Now, in our proof, we're essentially just going to show correspondences between the online and offline problem. So we first proved that Pareto efficiency in the offline problem will imply expost Pareto efficiency in our randomized allocation algorithm. Meanwhile, for fairness, for each pair of agents, the fairness guarantee that we have in the offline problem will actually determine the fairness guarantee we show in the online problem. So for the case of when I and j are in different cliques, we know that I is strongly envy-free towards j. And we can show this translates to envy-freeness with high probability in the online problem by arguing the expected envy, which will decrease linearly, will dominate the tails of the distribution. Now for the other case, if I and j are in the same clique, as mentioned before, they can be treated as a single agent. We modify the random allocation algorithm to treat cliques as one large combined agent. When an item is assigned to the clique, we do a form of round robin within the clique to guarantee an EF1 relationship in the online problem. And of course, there's some details there. Now, finally, I'll briefly discuss how we solve the offline problem. For this setting, with homogeneous divisible items, maximizing the product of utilities guarantees envy-freeness and Pareto efficiency. And maximizing the product of utilities is equivalent to solving an optimization problem referred to as the Eisenberg-Gale convex program, which we know how to solve in strongly polynomial time. Now, we'll start with the arbitrary solution to the convex program, which we know is envy-free and Pareto efficient. And we're going to repeatedly transfer items between agents to reach new solutions that contain more strong envy-freeness edges until we reach a CISEF allocation. Because it's still a solution, we'll get Pareto efficiency for free. For those of you familiar with solving Eisenberg-Gale convex programs, we work with familiar tools such as KKT conditions. Now, to summarize, first we introduced a range of adversaries for online fair division. For the adaptive and non-adaptive adversary, we show that fairness and efficiency are incompatible. In this case, even achieving a very weak notion of fairness, sublinear envy, requires giving up efficiency. Now, when items are drawn from distributions that don't vary over time, we show that we can achieve optimal fairness and efficiency. And along the way, to achieve this, we discussed solving a related offline allocation problem and a relaxed notion of strong envy-freeness for that offline setting. One limitation of our work is that for distributional adversaries, we assume the distribution is fixed and then do the analysis taking t to infinity. Suppose instead that the adversary distribution can depend on t. Then the problem becomes much more challenging. Recently, Bansal et al. Show O of log t upper bound for NV for two agents. And one possible open problem is whether we can get a similar result for fairness that also has a strong efficiency guarantee, such as Pareto efficiency. Thank you all for listening.